Look up at the night sky on a clear evening, past the city lights and the familiar patterns of constellations. Every single one of those points of light is a sun, a star. And for centuries, we could only wonder if any of them had planets of their own, other worlds circling in the darkness. But that wonder has now transformed into one of the most thrilling quests in human history, the search for life beyond our pale blue dot. Are we alone? This is perhaps the most profound question we can ask, and today we are closer than ever to finding an answer. Our journey begins with the discovery of exoplanets, worlds orbiting distant stars. We've moved from speculation to a catalogue of thousands, and hidden within that vast cosmic menagerie are the most promising candidates, the places where the conditions for life as we know it might just exist. This isn't science fiction anymore, it's the cutting edge of science itself. We are now galactic real estate agents, surveying the most habitable properties the universe has to offer. Think about that for a moment. We live in an age where we can analyze the atmosphere of a world hundreds of light years away. We can detect the subtle wobble of a star caused by the gravitational tug of an orbiting planet, or witness the tiny dip in starlight as that world passes in front of its sun. These techniques have unveiled an astonishing diversity of planets, scorching gas giants orbiting perilously close to their stars, frozen rogue worlds drifting in the interstellar void, and most tantalizingly, rocky planets nestled within the Goldilocks zone, that perfect region where temperatures might allow for liquid water to pool on the surface. Water, the essential ingredient for life on Earth, becomes our first clue in this cosmic detective story. But the story gets even richer. We're not just looking for Earth twins, we're considering worlds with subsurface oceans hidden beneath icy shells, planets locked in eternal twilight, and exotic environments that challenge our very definition of habitability. So prepare for a tour of the most incredible real estate in the galaxy. We are about to embark on a countdown of the top 30 planets that could host alien life. We will visit super-Earths with crushing gravity and thick atmospheres, wander the shores of possible water worlds, and peer into the mysteries of planets orbiting cool, stable red dwarf stars. This is a journey of imagination, guided by hard data and brilliant discovery. Each of these worlds tells a part of a much larger story, a narrative about our place in the cosmos and the potential for life to arise wherever conditions are right. The search for extraterrestrial life is a journey that speaks to something deep within us all, a blend of curiosity, hope, and the unshakable feeling that the universe is too vast, too grand for us to be the only ones here. So let's begin our exploration of these 30 promising worlds and see what wonders await. And so our countdown begins not in some far-flung corner of the galaxy, but right on our cosmic doorstep. A mere 4.2 light-years away, a distance that is simultaneously incomprehensibly vast and tantalizingly close in astronomical terms, orbits our very first candidate, Proxima Centauri b. This world circles Proxima Centauri, the smallest and coolest member of the triple star system that includes the brighter Alpha Centauri A and B. What makes this planet so immediately compelling is its location squarely within its star's habitable zone, that cherished region where temperatures could theoretically allow for liquid water to exist on the surface. With a mass estimated to be about 1.3 times that of Earth, it falls into the category of a rocky planet, a potential cousin to our own world. The proximity and these Earth-like qualities make it one of the most intensively studied exoplanets known to science. Yet, living next door to a red dwarf star like Proxima Centauri comes with a set of extraordinary challenges that paint a very different picture from our tranquil existence around the Sun. Red dwarfs are notoriously tempestuous, especially in their youth. Proxima Centauri is known to unleash violent stellar flares, eruptions of radiation that can be hundreds of times more powerful than anything our Sun produces. A planet like Proxima b, orbiting so close to its star to stay within the habitable zone, would be periodically bathed in deadly doses of X-rays and ultraviolet radiation, capable of stripping away our atmosphere and sterilizing the surface. This leads to another fundamental difference: tidal locking. Because the planet orbits so closely, gravitational forces have likely caused it to rotate in such a way that one hemisphere permanently faces the star, locked in an eternal, scorching day, while the opposite hemisphere is trapped in a perpetual frozen night. This presents a seemingly intractable problem for life, but nature is often more ingenious than our first assumptions. Scientists speculate that the most promising environment on such a world might not be on the day side or the night side, but precisely along the boundary between them, the terminator line. Imagine a narrow twilight band that circles the entire planet, where the fierce heat of the day gradually gives way to the deep chill of the night. In this perpetual dawn or dusk, temperatures could be just right for liquid water to persist. It's a world of eternal sunrise where any potential life would exist in a ring-shaped habitat, never seeing the star directly overhead or experiencing true darkness. The atmosphere, if it has managed to survive the flares, would be key, potentially circulating heat from the day side to the night side, creating dynamic weather patterns right in that habitable zone. While it may not be an Earth twin, Proxima Centauri b represents a fascinating and entirely new class of habitable environment, a testament to life's potential tenacity in the most unexpected of places. Moving from our nearest stellar neighbor, we venture just under 40 light-years away to a truly extraordinary planetary system that has captivated astronomers, TRAPPIST-1. This system is not just a star with a single promising world, but a veritable solar system in miniature, a tightly packed family of 7 rocky planets, each one remarkably close in size to Earth. The star at the center of it all is an ultra-cool red dwarf, much smaller and dimmer than our Sun. This characteristic is what makes the system so fascinating. Because the star is so faint, its habitable zone is incredibly close in. All 7 planets orbit their star at a distance smaller than Mercury's orbit around our Sun, creating a compact cosmic archipelago where a year on the outermost world passes in just a matter of Earth days. Within this unique family, one world stands out as a primary target in the search for life, TRAPPIST-1e. This planet is often described as the jewel in the crown of the system. It's almost exactly Earth's size and mass, suggesting a similar rocky composition. Most importantly, it orbits squarely in the middle of the star's habitable zone, placing it in the sweet spot where surface temperatures could be just right for liquid water to exist. But what truly ignites the imagination about TRAPPIST-1e is the possibility of a substantial atmosphere. A thick atmosphere could act as a global temperature regulator, distributing heat from the star around the planet and potentially creating a much more stable and Earth-like climate than we might find on a tidally locked world like Proxima b. This atmospheric blanket could be the key to protecting any potential life from the star's occasional flares and maintaining a temperate environment. Imagine standing on the surface of TRAPPIST-1e. The sky would be a sight unlike any we've ever witnessed. The parent star would appear about 3 times larger than our Sun does in our sky, glowing with a soft, dim, salmon-pink light. And because the other planets in the system are so close together, they would frequently appear in the sky as vivid, star-like points, some even showing distinct disks, much like we see our Moon. You might be able to see the cloud patterns or geological features of neighboring worlds with the naked eye, a celestial ballet of astonishing proximity. This very closeness also makes the TRAPPIST-1 system a perfect natural laboratory for science. Since all 7 planets formed from the same material around the same star, studying the differences in their atmospheres, why one might be a dry desert while another is a water world, can teach us fundamental rules about how planets evolve and what conditions lead to habitability. TRAPPIST-1e offers a vision of a world that, in many ways, feels familiar, yet exists within a planetary arrangement that is utterly alien. While TRAPPIST-1e captures our attention as a potential Earth analog, its siblings in the system, TRAPPIST-1f and TRAPPIST-1g, present equally compelling, though vastly different, possibilities for life. These two worlds demonstrate that habitability isn't a one-size-fits-all concept. It can manifest in a stunning variety of forms, even within the same stellar family. Located just a bit further out from their dim star, these planets occupy the cooler outer edge of the habitable zone, a placement that dramatically shapes their potential character. TRAPPIST-1f, receiving a little less stellar energy than its inner neighbor, might not be a world of surface oceans and balmy skies. Instead, scientists speculate it could be a vast, frozen globe, a cosmic iceball with a surface temperature far below freezing. But this doesn't rule it out as a lifeless world. In fact, it invites a fascinating comparison to some of the most promising locations right here in our own solar system, like Jupiter's moon Europa. The leading hypothesis is that TRAPPIST-1f could possess a thick, icy crust that acts as a protective shell, insulating a deep, global liquid water ocean beneath. This subsurface sea would be completely shielded from the stellar flares and radiation of its red dwarf sun, creating a dark, pressurized environment powered not by sunlight, but by geological heat from the planet's core. Life, if it exists there, would be utterly alien, thriving around hydrothermal vents on the seafloor in perpetual darkness, a scenario that mirrors some of the most extreme and ancient ecosystems found on Earth. Further out still lies TRAPPIST-1g, a world that tips the scales as one of the largest rocky planets in the system. Its greater size and mass suggest it could have held onto a much denser atmosphere than its companions. This thick atmospheric blanket becomes a crucial factor. It could efficiently trap what little heat it receives from the star, creating a powerful greenhouse effect that warms the planet's surface to potentially temperate levels. In this scenario, TRAPPIST-1g might not be an icy world at all, but a planet with liquid water oceans under a hazy, complex sky. Some models even suggest that its stronger gravity could lead to more active plate tectonics and a more robust magnetic field, both of which are thought to be beneficial for maintaining a stable environment over billions of years. This combination of factors leads to a provocative idea. TRAPPIST-1g could, in some ways, be more habitable than Earth, a super-Earth with greater geological stability and a more extensive habitable area. The true wonder of this system lies in the interplay between these worlds. Imagine the possibility that life, using basic chemical building blocks, could have arisen independently on multiple planets within this single family. Or, even more mind-boggling, consider the concept of lithopanspermia, the idea that life could be transferred between planets by meteorite impacts. A large asteroid strike on a life-bearing TRAPPIST-1e could eject rocky debris into space, and within the incredibly compact architecture of this system, it would be far easier for that material, potentially carrying microbial life, to travel to TRAPPIST-1f or TRAPPIST-1g than it is for material to travel between Earth and Mars. We aren't just looking at individual planets, but at a connected network of worlds, a celestial archipelago where the spark of life might have hopped from one island to another, creating a symphony of biological diversity all orbiting the same faint pink star. Leaving the tightly packed family of TRAPPIST-1 behind, we journey over 500 light-years away to a world that holds a special place in the history of exoplanet discovery. Kepler 186f wasn't just another entry in the growing catalogue of distant planets. It was a landmark. When it was confirmed in 2014, it became the very first planet we had ever found that was almost exactly the size of Earth and orbiting comfortably within its star's habitable zone. This was the moment the search for life beyond our solar system shifted from a theoretical possibility to a tangible reality. Before Kepler 186f, we knew of gas giants in habitable zones and planets larger than Earth, but finding a world so similar in stature to our own, perched in that just right region, was a definitive proof of concept. It told us that planets like ours are not cosmic rarities, but likely common throughout the galaxy. Kepler 186f orbits a star known as Kepler 186, a red dwarf that is smaller, cooler, and significantly dimmer than our Sun. The planet itself is about 10% larger than Earth, placing it firmly in the category of a rocky world rather than a gaseous one. A year on this distant world passes in just 130 Earth days, a relatively short orbit that is nevertheless situated at the outer edge of its star's habitable zone. This position is critical. It receives only about 1/3 of the stellar energy from its Sun that Earth gets from ours. You might picture a world in a perpetual state of twilight, where the sunlight is a deep, ruddy hue, casting long shadows across an alien landscape. The star in its sky would appear small and faint, glowing with a distinct crimson light. This unique lighting situation has profound implications for any potential life. Plants, or whatever passes for plant life there, would have evolved to photosynthesize using this predominantly red light. Instead of the lush green foliage we're familiar with, the landscape could be dominated by colors we can barely imagine. Shades of black, deep purple, or even infrared, pigments specially adapted to capture every available photon of that dim, red sunshine. The climate would likely be much cooler than Earth's on average, potentially leading to a world where liquid water exists, but where large ice caps might extend far from the poles. The planet's axial tilt and rotation are still unknown, but if it has a stable climate and a protective atmosphere, it could host environments where life has found a way to thrive. The true legacy of Kepler 186f is one of inspiration and direction. Its discovery by the Kepler Space Telescope validated the mission's core goal, to determine how common Earth-like planets are in our galaxy. By finding one, it strongly suggested there are millions more waiting to be discovered. It expanded our definition of a habitable environment, showing that life could potentially take root under the gentle glow of a red sun, in conditions that are quieter and more subdued than our own vibrant, sun-drenched world. Kepler 186f stands as a quiet pioneer, a distant cousin to Earth that forever changed our perspective and fueled the optimistic belief that we are living in a universe teeming with worlds, each with its own story to tell. After exploring the possibilities of planets around red dwarf stars, our search leads us to a world that feels distinctly more familiar, almost like a glimpse into a potential future for our own planet. Meet Kepler 452b, a discovery that sent ripples of excitement through the scientific community for one compelling reason. It orbits a star that is a near twin to our own Sun. This is not a turbulent red dwarf, but a stable G-type star, bathing its planetary family in a warm, yellow light very similar to what we experience here on Earth. This star, Kepler 452, is about 1.5 billion years older than our Sun, meaning the system has had an immense head start in the cosmic race for life. The planet itself, Kepler 452b, resides squarely within the habitable zone, earning it the nickname Earth's cousin or even Earth 2.0, though its story is more complex than a simple mirror image. The numbers surrounding this world are staggering and contribute significantly to its intrigue. A full year on Kepler 452b lasts only 385 days, a mere 20 days longer than our own annual journey around the Sun. But the most profound figure is 6 billion. That is the estimated amount of time this planet has spent orbiting within its star's habitable zone. To put that in perspective, life on Earth needed roughly 1 billion years to emerge from the primordial soup. Kepler 452b has had 6 times that long. Imagine the evolutionary pathways that could have unfolded over such an immense timescale. Simple microbial life would have had an almost unimaginable head start to develop into complex multicellular organisms and perhaps even intelligence. An older, more stable star provides a far less volatile environment than a young red dwarf, offering a steady, consistent energy source for billions of years longer than Earth has even existed. Yet the super-Earth classification of Kepler 452b introduces a fascinating set of variables. It is about 60% larger in diameter than Earth, which suggests a mass several times greater. This greater mass translates directly to a stronger surface gravity. Walking on this world would feel like carrying a significant extra weight at all times, which would shape not only the potential life forms but the very geology of the planet. A thicker atmosphere is almost a certainty, as the stronger gravity would be more effective at holding onto gases. This is where the planet's story branches into two very different possibilities. On one hand, that thick atmosphere could act as a perfect insulating blanket, creating a global tropical paradise with lush planet-wide forests and vast warm oceans. It could be a world of stunning biological diversity, a hyper-Earth where life has filled every conceivable niche. The other, more cautionary possibility is a runaway greenhouse effect. Venus, in our own solar system, stands as a stark reminder of how this can go wrong. If the atmosphere of Kepler 452b is too thick with heat-trapping gases like carbon dioxide, the surface temperature could have soared over the billions of years, boiling away any initial oceans and creating a hellish high-pressure environment. The planet's oldest star would have grown brighter over time, potentially pushing a delicate climate system over the edge. So is Kepler 452b a verdant, ancient jungle world teeming with life, or a scorched and sterile wasteland? It represents a critical question in astrobiology. Does spending more time in the habitable zone guarantee a living world, or does it simply provide more opportunity for a climate to destabilize? This distant cousin serves as a crucial test case for understanding the long-term fate of Earth-like planets, making it a prime target for future telescopes that will one day analyze its atmosphere for the chemical signs of life or its absence. Shifting our focus from planets around sun-like stars, we return to the realm of red dwarfs to encounter two super-Earths that have become absolute priorities for astronomers, not just for their location but for their profound physical characteristics. These are not merely points of light, they are worlds with defined personalities, and the first of these, LHS 1140b, stands out as a particularly dense and intriguing candidate. Orbiting a remarkably quiet and stable red dwarf located about 49 light-years away, this planet presents a set of features that make it one of the most promising targets in the entire sky. Its most defining quality is its mass and density. While it is about 1.7 times the size of Earth, its mass is over 6 times greater. This incredible heft means LHS 1140b is not a puffy, gaseous mini-Neptune. It is a solid, rocky world of extraordinary proportions, a true mega-Earth with a composition likely rich in iron and other heavy elements. The implications of this density are fascinating. A planet this massive would have a surface gravity significantly stronger than our own. The experience of standing on its surface, if it were possible, would be one of immense weight, a force that would shape everything from the planet's geology to any potential life forms that might evolve there. Mountains could not rise as high as they do on Earth, as they would collapse under their own weight, leading to a world with a relatively smooth, low-lying topography. More importantly, this powerful gravity acts as a superb anchor for an atmosphere. It would be exceptionally difficult for gases to escape into space, suggesting that LHS 1140b could have maintained a thick, stable atmosphere over billions of years. This, combined with its orbit squarely within the habitable zone of its placid parent star, creates a compelling package. The star's quiet nature means it lacks the violent flares that threaten planets like Proxima Centauri b, offering a far more stable and benign environment. For scientists using the James Webb Space Telescope, LHS 1140b is a dream target. Its density suggests a solid surface, its gravity hints at a substantial atmosphere, and its calm star provides a clear backdrop against which to study that atmosphere for the telltale biosignatures of life. Our next destination, K2-18b, orbiting a red dwarf star 120 light-years away, made history for a different, breathtaking reason. While many planets on our list are promising based on their position and size, K2-18b gave us a tangible, game-changing piece of evidence. In 2019, astronomers analyzing data from the Hubble Space Telescope announced they had detected water vapor in its atmosphere. This was a monumental first. It was the first and only time water vapor had been identified in the atmosphere of a planet residing in its star's habitable zone. A planet that is also classified as a super-Earth, falling somewhere between the size of Earth and Neptune. This discovery instantly propelled K2-18b into the spotlight, but it also opened up a heated and fascinating debate about the planet's very nature. The presence of water vapor is tantalizing, but what does the surface of this world actually look like? The leading hypothesis is that K2-18b is not a rocky world like Earth or LHS 1140b, but a water world or even a Hycean world, a planet with a global, planet-wide ocean hundreds of kilometers deep beneath a thick, hydrogen-rich atmosphere. In this scenario, there would be no land masses at all. The entire surface would be a single, endless ocean, with pressures at depth becoming so immense that water could form exotic states of ice like hot, high-pressure ice at the very bottom of the sea. The conditions in its atmosphere might be temperate, but the surface would be an entirely aquatic environment. The sheer amount of water present on such a world is both a blessing and a curse for life. On one hand, water is the universal solvent essential for life as we know it. A global ocean provides a vast, interconnected habitat. On the other hand, without a rocky seabed for geology to interact with the water, some of the key nutrients thought to be necessary for life's origin might be scarce. Furthermore, the immense pressure and the potential lack of a solid core could hinder the geological activity that helps regulate a planet's climate over long timescales. Yet the discovery on K2-18b was a proof of concept. It demonstrated that we possess the technology to detect water, the key ingredient for life, on worlds far beyond our solar system. It transformed the search from one of theoretical modeling to one of direct atmospheric interrogation, setting the stage for future discoveries that will not only confirm the presence of water, but also search for the gases that life itself produces. Continuing our journey through the catalogue of promising worlds, we arrive at GJ357d, a super-Earth whose discovery by NASA test satellite presents a fascinating puzzle for astrobiologists. Located just 31 light-years away, a stone's throw in galactic terms, this planet orbits a small, quiet M-type dwarf star. What makes GJ357d so compelling is its position at the very outer fringe of its system's habitable zone. It receives a meager amount of stellar energy, only about a third of what Earth gets from the Sun. Based on that fact alone, you might picture a frozen, barren world. However, its physical properties open the door to a much more intriguing possibility. With a mass at least 6 times that of Earth, this is a substantial world, and that substantial nature is the key to its potential. A planet of this size has the gravitational strength to hold onto a significant atmosphere, and the nature of that atmosphere becomes the single most important factor determining whether this distant globe is an ice lock or a temperate haven. This is where the scenario splits into 2 dramatically different futures, hinging entirely on atmospheric composition. In one model, GJ357d could possess a thin atmosphere similar to Mars. Under those conditions, with so little heat arriving from its dim star, the surface would be profoundly cold, likely well below freezing, making the existence of liquid water on the surface virtually impossible. It would be a silent, frozen sphere, but the alternative is far more exciting. If GJ357d has managed to acquire and retain a thick, hydrogen-rich atmosphere, the entire equation changes. Hydrogen is a powerful greenhouse gas. A dense blanket of hydrogen and helium could act as an incredibly effective insulating layer, trapping the tiny amount of incoming stellar radiation and preventing it from escaping back into space. This greenhouse effect could raise surface temperatures to levels comfortably above the freezing point of water. In this second scenario, GJ357d could be a vast water world, a global ocean planet shrouded under a deep, hazy atmosphere. There would be no continents, no rocky shorelines, just an endless, dark sea stretching from pole to pole. The surface would be shrouded in perpetual twilight, with the small, reddish parent star providing only a dim glow. Life in such an environment would be entirely aquatic, existing in the depths of this global ocean. The pressures at the bottom would be immense, potentially creating layers where water transitions into exotic forms of ice. Yet near the surface, conditions could be suitable for microbial life or even more complex organisms. This concept of a planet being warmed not primarily by its star, but by its own atmosphere, expands our understanding of where habitable conditions can arise. It suggests that even worlds on the chilly outskirts of their stellar systems cannot be ruled out. GJ357d stands as a powerful reminder that a planet's true character is not defined by distance alone, but by the complex and dynamic interplay between its geology, its mass, and the protective envelope of gases it wears. Now we turn our attention to a star so faint and small it was only discovered in 2003, yet it hosts one of the most Earth-like planets we have ever found. Meet Tigodon's star, an ancient red dwarf located a mere 12 light-years away. It's a stellar lightweight with only about 8% of our Sun's mass, and it glows with a feeble warmth that makes it invisible to the naked eye. But orbiting this diminutive Sun is a world that has captured the imagination of astronomers, Tigodon's star B. What makes this planet so remarkable is its incredibly high Earth Similarity Index, or ESSI. This index is a scale that compares an exoplanet's properties, like its size and the amount of energy it receives from its star, directly to Earth. A score of 1.0 would be a perfect Earth twin. Tigodon's star B scores an impressive 0.95, placing it among the top contenders for a world that could have surface conditions strikingly similar to our own. The environment on this world, however, would be profoundly alien. Because its parent star is so dim, the habitable zone is incredibly close in. Tigodon's star B orbits at a distance where a complete revolution, an entire year, takes just 4.9 Earth days. This proximity almost certainly means the planet is tidally locked, with one hemisphere perpetually bathed in the dim, reddish light of its star, and the other plunged into eternal, frigid darkness. The concept of a day-night cycle as we know it simply wouldn't exist. Instead, the most habitable region would be the narrow band of twilight that circles the globe, the Terminator line. Here, in a perpetual state of dawn or dusk, temperatures could be moderate enough for liquid water to exist. Any potential life would be confined to this ring-shaped habitat, with the small, dark red star forever hanging motionless on the horizon. This unique setup presents both challenges and opportunities for life. The constant, low-level red light would drive a very different form of photosynthesis. Plant life, if it exists, would likely be shades of black or deep purple to absorb every possible photon. The lack of a rotating magnetic field might make the planet more vulnerable to stellar radiation. But Tigodon's star is notably quiet and stable for its class, offering a calmer environment than the flare-prone Proxima Centauri. After billions of years of stability, life in that twilight ring could have evolved into complex and strange forms, perfectly adapted to a world without sunrise or sunset, where the only constant is a faint crimson sun fixed in the sky. Tigodon's star B challenges our Earth-centric view of habitability, suggesting that even under these extreme conditions, the recipe for life might still find a way to succeed. Now we venture to a neighbor that is practically in our cosmic backyard, a world so close that its star is visible from Earth with a simple telescope. Just 14 light-years away, Wolf 1061c holds the distinction of being one of the nearest known exoplanets to orbit within its star's habitable zone. This proximity makes it an incredibly valuable target for study, a nearby laboratory for testing our theories about what makes a world livable. The planet is part of a multi-planet system circling a stable red dwarf star, and it sits in a particularly precarious and revealing position. Wolf 1061c doesn't orbit in the comfortable middle of the habitable zone. Instead, it hugs the inner edge closer to its sun. This placement puts it in a delicate balancing act, a celestial tightrope walk between two dramatically different fates. On one side of that balance is the possibility of a temperate, Earth-like world. With a mass a little over 4 times that of Earth, it falls squarely into the super-Earth category, suggesting a rocky composition and enough gravity to hold onto a substantial atmosphere. If that atmosphere has the right composition, a mix of nitrogen, oxygen, and just the right amount of greenhouse gases, it could create a stable climate where liquid water flows on the surface. Its closer orbit means a year flashes by in only 18 Earth days, but that doesn't necessarily preclude life. The planet's potential for tidal locking, with one side always facing the star, could create that familiar twilight band of habitability we've seen on other red dwarf worlds. In this optimistic scenario, Wolf 1061c could be a world of deep red landscapes and strange life forms adapted to its unique rhythm. However, the other side of that balance is a far more ominous possibility, one that serves as a stark warning from our own solar system. Because it orbits so close to the inner edge of the habitable zone, Wolf 1061c is highly susceptible to a runaway greenhouse effect. This is the same process that scientists believe transformed Venus from a world that might have once had oceans into the scorching, acidic hellscape it is today. Here's how it could happen. If the planet's initial atmosphere contained too much carbon dioxide or water vapor, those gases would trap increasing amounts of heat from the star. This rising temperature would cause more water to evaporate from the oceans, and since water vapor is itself a potent greenhouse gas, the effect would amplify itself in a vicious cycle. The temperature would soar uncontrollably, eventually boiling the oceans away entirely and leaving behind a thick, crushing atmosphere dominated by carbon dioxide, with surface temperatures hot enough to melt lead. This is why Wolf 1061c is such a crucial case study. It represents a critical boundary condition for life. Is it a world that has managed to achieve a stable climate for billions of years? Or is it a cautionary tale of a planet that ventured too close to its sun and paid the ultimate price? The answer lies in its atmosphere, and future observations with powerful telescopes like the James Webb will be aimed squarely at detecting its chemical composition. Finding signs of water vapor would be a promising indicator, while detecting an atmosphere thick with carbon dioxide and devoid of water would strongly suggest a Venus-like fate. This nearby world, therefore, is more than just another candidate. It's a key to understanding the fine line between a habitable paradise and an uninhabitable furnace, helping us define the exact boundaries of the Goldilocks zone itself. The Kepler Space Telescope was a factory of discovery, revealing thousands of worlds in its stare towards the constellations Cygnus and Lyra. Among this incredible bounty, a few systems stand out for their complexity and promise, and the Kepler 62 system is a prime example. Located about 1,200 light-years away, this star, slightly smaller and cooler than our Sun, hosts a family of 5 known planets. 2 of these siblings, Kepler 62e and Kepler 62f, have captivated astronomers as a fascinating pair of potentially habitable worlds orbiting the same sun, offering a chance to compare 2 different flavors of planetary environment within a single family. Kepler 62e is the inner of the 2 habitable zone planets. It's a super-Earth about 60% larger than our own world, and it orbits closer to its star, completing a year in just 122 days. The energy it receives is somewhat higher than what Earth gets, placing it on the warmer edge of the habitable zone. This has led to widespread speculation that Kepler 62e could be a water world, a planet completely engulfed by a global deep ocean. Imagine a world with no visible land where the entire surface is a single, vast body of water. The sky might be filled with thick clouds and frequent planet-wide storms, with the ocean depths hiding mysteries we can only guess at. Life on such a world would be exclusively aquatic, potentially evolving in the deep, dark waters around hydrothermal vents, or flourishing in the sunlit upper layers of the sea. The greater gravity of this super-Earth would create immense pressures at the ocean floor, possibly leading to the formation of exotic forms of ice, even in relatively warm water, creating a truly alien seascape. Its sibling, Kepler 62f, presents a strikingly different picture. Orbiting further out with a 267-day year, it receives only about 41% of the stellar energy that Earth does. Most importantly, it is almost exactly Earth size. This combination makes it one of the most Earth-like planets ever discovered in terms of both physical dimensions and its position relative to its star. However, its location on the cooler, outer fringe of the habitable zone suggests a world that could be considerably chillier than our own. Without a sufficiently thick atmosphere to trap heat, Kepler 62f might be an ice-covered globe, a snowball world where life would be confined to subsurface oceans or isolated areas near the equator. But if it possesses a dense atmosphere rich in greenhouse gases like carbon dioxide, that same atmosphere could act as a planetary blanket, raising temperatures to create a more temperate and perhaps even comfortable environment. The possibility of these two contrasting worlds, a warm water world and a cooler, potentially Earth-sized planet existing in the same system, is a powerful reminder of the diversity of conditions that can arise around a single star. Moving to another standout from the Kepler catalogue, we find Kepler 442b, a world that orbits a star slightly smaller than our Sun, about 1,200 light-years away. What makes this planet particularly interesting is the amount of light it receives from its parent star, about 70% of what Earth gets. This places it in a fascinating climatic sweet spot. It's not so close to the star that it risks a runaway greenhouse effect, nor is it so far out that it requires an exceptionally thick atmosphere to avoid freezing solid. Scientists have calculated that Kepler 442b has a high probability of having a rocky surface, and its receipt of stellar energy is considered, by some metrics, even more optimal for photosynthesis than what Earth receives. This doesn't guarantee life, of course, but it suggests the planet has the right foundational conditions for a temperate climate. The environment on Kepler 442b would likely be cooler on average than Earth's, perhaps resembling a global autumn or a perpetual spring. Imagine landscapes with forests adapted to lower light levels, possibly showing darker foliage to absorb every available photon. Its longer year, lasting 112 Earth days, and its status as a super-Earth about 30% larger than our planet, suggest a world with stronger gravity and potentially more active geology. This trio of worlds, the aquatic potential of Kepler 62e, the Earth-sized promise of Kepler 62f, and the optimally lit, rocky nature of Kepler 442b exemplify the different pathways to habitability that the Kepler mission revealed. They remain high-priority targets because each represents a key variable in the grand experiment of planet formation: size, atmospheric composition, and stellar energy input. Future telescopes will aim their instruments at these distant points of light, seeking the subtle chemical fingerprints in their atmospheres that could tell us if any of these promising environments have actually given rise to life. But what if you could look up and see not one, but 3 suns in your sky? Our next destination offers precisely that spectacular vista. welcome to GJ667cc, a world that turns science fiction into scientific reality. Located a relatively close 23.6 light-years away in the constellation of Scorpius, this planet is part of a truly extraordinary stellar arrangement, a triple star system. GJ667cc orbits the smallest of the three stars, a red dwarf designated GJ667c. But the other two stars, a pair of orange dwarfs locked in a tight dance with each other, are also gravitationally bound to the system. From the surface of this distant world, those two additional suns would appear in the sky as incredibly bright, piercing points of light, shining with a combined luminosity about as bright as our own full moon. The primary red dwarf sun would hang there as a large, dim, reddish disk, while its two stellar companions provided a constant, dazzling secondary light source, casting complex and ever-changing shadows across the landscape. Beyond this breathtaking celestial display, GJ667cc is a serious contender in the search for life. It's a super-Earth with a mass at least 3.7 times that of our own planet, suggesting a solid, rocky surface. Most importantly, it orbits squarely within the habitable zone of its parent red dwarf. A year on this world is a mere 28 Earth days, but that close orbit comes with the potential challenge of tidal locking. However, the presence of the other two stars adds a fascinating wrinkle to its climate. While they are too far away to provide significant warming, their gravitational influence could have played a crucial role during the planet's formation, potentially enriching it with a wealth of water-bearing asteroids and comets. This raises the tantalizing possibility that GJ667cc is a water-rich world. The long-term stability of such a complex system is a subject of intense study. With three stars pulling on each other and the planet, the gravitational forces at play are incredibly intricate. While current models suggest the planet's orbit is stable over millions and billions of years, subtle interactions could cause its path to slowly wobble or change shape. This phenomenon, known as orbital evolution, could gently push the planet slightly closer to or further from its star over cosmic timescales. For a world perched in the habitable zone, even a small shift could have dramatic consequences, potentially nudging it out of that life-friendly region or, conversely, into a more optimal position. This introduces the concept of a habitable epoch, a period of time, perhaps lasting for 1 billion years or more, when conditions are just right for life to arise and evolve, even if they don't last forever. GJ667cc challenges us to think not just about where life could exist now, but about the dynamic history of planetary systems and the windows of opportunity that might open and close throughout the life of a star. Now, a fascinating case of celestial ambiguity takes us to a world whose very existence has been a subject of scientific debate. Planet number 16 on our list is HD 40307G, a super-Earth orbiting a star about 42 light-years away in the constellation Pictor. The star itself is somewhat smaller and cooler than our Sun, a quiet K-type dwarf that offers a stable base of energy. The planet, however, is anything but straightforward. Initial discoveries suggested HD 40307G was a promising world, a planet with a mass at least 7 times that of Earth, comfortably situated within its star's habitable zone. This placement would make it a prime candidate, a large, rocky world with the potential for a thick atmosphere and surface conditions suitable for liquid water. But in the world of exoplanet science, initial data is often just the beginning of the story, and further analysis has painted a more complex and intriguing picture. The central controversy surrounding this world revolves around the shape of its orbit. While planets in our solar system, like Earth, have orbits that are nearly circular, this is not a universal rule. Some studies of HD 40307G suggest that its path around its star might be significantly elliptical, more like a stretched oval than a gentle circle. This single characteristic would completely redefine the nature of this world. Instead of enjoying a relatively constant distance from its sun, the planet would experience dramatic swings. At its closest approach, it would be bombarded with intense stellar radiation, causing temperatures to soar. Then, as it swung out to the far point of its orbit, it would enter a long, deep freeze, receiving only a fraction of that energy. A year on this world would not be a cycle of mild seasons, but a violent pendulum swing between two extreme climatic states. Imagine the challenges this presents for life. Such extreme seasonality would be unlike anything experienced on Earth. The planet might spend a brief, scorching summer with any surface water boiling away into a thick, steamy atmosphere, followed by an immensely long global winter where the entire world freezes solid. This kind of environment seems, at first glance, utterly hostile. Yet, astrobiologists are deeply interested in these exact conditions because they force us to expand our thinking. Life is remarkably tenacious, and such a cycle could drive astonishing evolutionary adaptations. Perhaps life on HD 40307G would not exist on the surface at all, but deep underground, in vast cave networks insulated from the temperature extremes above. Microbial life could enter a state of suspended animation during the deep freeze, only to reactivate and flourish during the short, hot summer when liquid water might briefly flow on the surface. Alternatively, a thick global ocean could act as a massive thermal buffer. The surface might freeze over during the long winter, but the depths of the ocean could remain liquid, protected by a ceiling of ice. Life could thrive in this dark, aquatic refuge, perhaps relying on chemical energy from hydrothermal vents, completely independent of the chaotic conditions on the surface. The intense seasonal change could even be a catalyst for biodiversity, creating distinct ecological niches that species must rapidly adapt to fill. HD 40307G, whether it proves to have a circular or elliptical orbit, stands as a powerful reminder that habitability is not a simple on-off switch. It is a spectrum of possibilities, and worlds that seem hostile by Earth standards may harbor life forms that have learned to not just survive, but to thrive on the edge of chaos. Now we turn our attention to a star that has been a beacon in our night sky and in our imaginations for generations. Tau Ceti, a solitary sun-like star just 12 light-years away, is visible to the naked eye from a dark location. It has featured prominently in science fiction for decades, often portrayed as the home of an advanced alien civilization. The discovery of planets around this iconic star was a milestone, and one of them, Tau Ceti e, presents a fascinating and complex picture of potential habitability. This world is a super-Earth with a mass at least 4 times that of our own planet, and it orbits remarkably close to its star, completing a full revolution in just 168 Earth days. This proximity places it right on the inner edge of Tau Ceti's habitable zone, a location that makes its climate a subject of intense debate. The defining characteristic of Tau Ceti e is heat. Receiving about 60% more stellar energy than Earth, this planet walks a fine line between being a warm, tropical world and a scorching inferno. The outcome hinges almost entirely on the nature of its atmosphere. If Tau Ceti e has a relatively thin atmosphere, similar to Earth's, the intense sunlight could still create surface temperatures far too high for liquid water to exist, potentially making it a dry, Venus-like desert. However, if it possesses a thick, reflective cloud cover or an atmosphere with a different composition that effectively deflects some of that incoming radiation, it could achieve a more temperate balance. The stronger gravity of this super-Earth makes a substantial atmosphere more likely, as it would be better at holding onto gases over billions of years. This creates a scenario where Tau Ceti e could be a world of extreme weather, with powerful greenhouse effects creating a global, steamy environment, but one where life in the oceans or in shaded regions might still find a way to persist. But there is another, more dramatic factor shaping the destiny of this world, one that sets the entire Tau Ceti system apart. Surrounding the star is an immense and massive debris disk, a vast belt of asteroids, comets, and dust left over from the system's formation. This disk contains far more material than the similar Kuiper belt in our own solar system, and this abundance tells a story of a much more violent celestial neighborhood. For any planet orbiting within this disk, the rate of asteroid and comet impacts would be catastrophic, estimated to be as much as 10 times higher than the bombardment rate Earth experiences. This constant barrage presents a profound paradox for the possibility of life. On one hand, these impacts are agents of destruction on a global scale. A large enough asteroid strike can vaporize oceans, fill the atmosphere with dust, and trigger extinction-level events. If such impacts are frequent, they could act as a cosmic reset button, repeatedly wiping the slate clean just as life begins to gain a foothold. Complex multicellular life, which on Earth required hundreds of millions of years of relative stability to evolve, might never get a chance to develop under such chaotic conditions. The surface of Tau Ceti E could be a scarred landscape, bearing the fresh craters of recent impacts alongside the ancient ruins of civilizations that never were. Yet, on the other hand, these same celestial projectiles are also the deliverers of life's essential ingredients. It is believed that asteroids and comets were crucial in bringing water and complex organic compounds, the building blocks of life, to the early Earth. In the Tau Ceti system, this delivery service is operating at an industrial scale. The constant influx of icy comets could have provided Tau Ceti E with oceans far deeper than our own, making it a truly water-rich world. The frequent impacts would also churn the planet's crust, driving geological activity and cycling nutrients essential for biochemistry. Life, in its simplest, most resilient microbial forms, might not only survive these impacts but could actually thrive in the aftermath, using the chemical energy released by the collisions. Tau Ceti E, therefore, forces us to confront a difficult question. Is a quiet, stable system like our own necessary for life to flourish? Or can it arise and persist in a cosmic shooting gallery, forever dancing between creation and destruction? This world is a test case for the resilience of life itself, a reminder that the path to biology may be as violent as it is wondrous. The Kepler mission's legacy extends far beyond its initial groundbreaking discoveries, continuing to unveil worlds that push the boundaries of what we consider habitable. Among these later findings, 2 planets stand out for the unique questions they raise. First is Kepler 1638b, a world that orbits a star remarkably similar to our own Sun. This alone makes it a significant target. Many of the most promising planets we've discussed orbit red dwarfs, stars with tempestuous youth and potential tidal locking issues. But Kepler 1638b offers a different vision. It's a super-Earth about 60% larger than our planet, and it resides squarely in the middle of its sun-like star's habitable zone. A year on this world lasts 259 Earth days, not too dissimilar from our own, and it receives a level of stellar energy very close to what Earth enjoys. This combination of a stable, familiar star and an optimal orbital position suggests a world with a strong potential for a temperate climate. The greater size and mass point to a robust gravity that could maintain a substantial atmosphere, potentially creating an environment where liquid water could flow freely on the surface. It represents the kind of world we instinctively imagine when we think of an Earth twin, a planet with a yellow sun in its sky, experiencing seasons, and orbiting in a calm, mature system that has had billions of years for life to potentially emerge. In stark contrast to this familiar picture, we have Kepler 1544b. This planet tells a different part of the Kepler story, one that emphasizes the critical role of a world's atmosphere. Kepler 1544b orbits a star slightly smaller than our Sun. but its most defining characteristic is its long orbital period. A single year on this world lasts 168 days, which places it much further from its star than Earth is from the Sun. As a result, it receives a similar amount of stellar energy as Mars does in our own solar system. At first glance, that might seem to rule it out. Mars is a frozen, desert world. However, this is where planetary science becomes so fascinating. A planet's surface temperature is not determined by distance alone. It is dramatically shaped by the insulating properties of its atmosphere. Mars has a very thin atmosphere, so it cannot retain heat, but Kepler 1544b is a super-Earth with about twice the radius of our planet. That greater size implies a stronger gravitational pull, one perfectly capable of holding onto a dense, thick atmosphere. If this planet possesses such an atmospheric blanket, the entire equation changes. A thick atmosphere rich in greenhouse gases like carbon dioxide or methane could trap the incoming stellar radiation extremely effectively, creating a powerful greenhouse effect. This would act as a global heating system, raising surface temperatures well above what simple distance calculations would suggest. In this scenario, Kepler 1544b could be a surprisingly temperate world, perhaps even warmer than Earth, with liquid water oceans despite its distant orbit. It might be a planet shrouded in perpetual, high-altitude clouds with a hazy orange sky and a climate more uniform than our own. This possibility forces us to reconsider the outer boundaries of the habitable zone. It demonstrates that a world that appears on paper to be too cold might in fact be a balmy, water-rich environment, all thanks to the invisible jacket of gases that surrounds it. The key to unlocking its true nature lies in analyzing the composition of that very atmosphere, a task for the next generation of space telescopes. Together, these two worlds exemplify the incredible diversity the Kepler mission revealed. We moved from a simple search for Earth twins to a fuller appreciation of the vast spectrum of planetary environments. The catalogue is not just a list of names and distances, it is a gallery of possibilities. It contains water worlds like K218b, tidally locked twilight planets like those in the TRAPPIST-1 system, ancient worlds like Kepler 452b, and atmospheric wild cards like Kepler 1544b. Each discovery added a new variable to our understanding of habitability, teaching us that life's potential is not confined to a narrow set of conditions. It can persist in eternal dusk beneath icy shells or under the warmth of a yellow sun. The true legacy of Kepler is this expanded perspective, this realization that the universe is a laboratory for planet building on a scale we are only beginning to comprehend, with each new world offering a unique chapter in the story of how life might find a way. The journey of discovery is not always a straight line, and sometimes the most tantalizing targets on our list are the ones that remain just out of reach, their very existence a subject of intense scientific debate. This brings us to the fascinating and controversial case of JJ581g, a world that, if confirmed, would be a landmark discovery. Announced in 2010, this planet was proposed to orbit the red dwarf star JJ581, located a mere 20 light-years away. What made the announcement so electrifying was the claim that JJ581g was a rocky world with a mass about 3 to 4 times that of Earth, and that it orbited squarely in the middle of its star's habitable zone. For a brief, thrilling moment, it seemed we had found one of the first and closest potentially Earth-like worlds. However, the initial excitement was soon met with skepticism. The detection of exoplanets, especially around small, jittery red dwarfs, is an incredible technical challenge. The method used to find JJ581g was the radial velocity technique, which measures the subtle wobble of a star caused by the gravitational tug of an orbiting planet. The signal of this particular wobble was incredibly faint, buried within the complex data of the star's own activity. other teams of astronomers analyzing the same data and additional observations struggled to find the same signal. Some concluded that what was interpreted as a planet's pull could actually be patterns caused by the star's magnetic cycles and star spots. This is the rigorous and sometimes frustrating nature of the scientific process. An initial discovery is a hypothesis, an invitation for the global community to test, challenge, and attempt to verify the finding. In the case of GJ581g, that verification has remained elusive, leaving the planet in a state of limbo, neither confirmed nor entirely ruled out. This ongoing controversy makes GJ581g a perfect case study for how exoplanet science works. It highlights the frontier nature of this field where we are pushing our instruments to their absolute limits. Discovering a small, rocky world in the habitable zone of a distant star is like trying to hear a whisper in a hurricane. The star itself creates a tremendous amount of noise, and separating the faint signature of a planet from that stellar cacophony requires immense statistical care and multiple independent observations. The debate over this world is not a sign of failure, but a sign of a healthy, critical scientific discipline. It forces refinements in data analysis techniques and drives the development of more powerful telescopes. The goal is not to prove a discovery right, but to arrive at a conclusion that is supported by the best available evidence, no matter how long that takes. Let's consider for a moment the profound implications if GJ581g were to be definitively confirmed. A rocky, potentially habitable world just 20 light-years away would instantly become the #1 target for the next century of astronomical research. Its proximity would place it within the reach of planned future instruments designed to directly image exoplanets. Instead of just inferring its existence through a star's wobble, we might one day see it as a faint, pale blue dot next to its reddish sun. We could analyze its atmosphere for signs of oxygen, methane, and other potential biosignatures. It would transform the search for life from a statistical exercise into a focused investigation of a specific, nearby world. The confirmation of GJ581g would tell us that such worlds are not only common, but that one exists right in our immediate cosmic neighborhood, making the dream of detecting signs of life elsewhere in the galaxy feel suddenly, tangibly within our grasp. This lingering possibility, this what if, is what keeps GJ581g firmly on our list, a ghost in the data machine that continues to inspire and challenge us to look deeper. Continuing our exploration of Kepler's remarkable legacy, we come to a world that exemplifies the telescope's power to find planets with a delicate balance of Earth-like qualities. Kepler 1229b orbits a red dwarf star about 770 light-years away, and what makes it so compelling is its physical proportions. With a radius estimated to be only slightly larger than Earth's, it is one of the closest matches to our own world's size that we have found within a habitable zone. This suggests a high probability of a rocky composition, a terrestrial landscape of mountains, valleys, and potentially basins that could hold liquid water. But the true key to its potential lies in the amount of energy it receives from its faint crimson sun. Kepler 1229b basks in about 70% of the stellar flux that Earth gets from our sun. This specific figure places it in a particularly interesting climatic sweet spot, not too hot and not too cold, but leaning towards a cooler, more stable environment. You might picture this distant world as a planet of dramatic contrasts. With its lower energy input, global average temperatures would likely be significantly cooler than Earth. This could result in a world where vast ice caps extend far from the poles, covering large portions of the surface in gleaming white glaciers. These immense sheets of ice would reflect a great deal of sunlight back into space, helping to maintain the planet's overall cool temperature. Yet, in the band around the equator, where stellar energy is most direct, temperatures could be warm enough to maintain open bodies of liquid water. This creates a vision of a world not unlike Earth during its ice ages, where life persisted and even thrived in refuges between the ice. The equatorial regions could be a belt of relative warmth, with deep blue oceans surrounded by icy shores, a haven for any potential biology. The climate might be dominated by powerful weather systems generated by the temperature difference between the frigid poles and the temperate equator, leading to strong winds and persistent cloud cover. The possibility of tidal locking adds another layer of intrigue. If one hemisphere permanently faces the star, the climate would be even more extreme, but also potentially more stable. The day side could host a permanent, slushy ocean under a dim red sun, while the night side would be a global, frozen desert. The most habitable region would again be the terminator line, the twilight zone where ice from the night side slowly melts under the weak warmth of the eternal sunrise. Whether it rotates or is locked, Kepler 1229b presents a compelling case for a cold but clement world. It teaches us that habitability does not require a tropical paradise. It can exist in a quiet, frozen state where life clings to the edges of the ice, much like the microbial communities found in Earth's own polar regions. This world is a testament to the idea that life is tenacious, capable of persisting in environments we might initially consider marginal, as long as the fundamental ingredient of liquid water is present somewhere on the globe. This brings us to a world that highlights a critical factor often overlooked in the search for habitable planets: the temperament of the star itself. Located just 11 light-years away, Ross 128b orbits a red dwarf that stands in stark contrast to the volatile nature of Proxima Centauri. While many red dwarfs are known for their fiery youth and frequent planet-sterilizing flares, Ross 128 is a paragon of stellar tranquility. It is what astronomers call an inactive star, exhibiting remarkably low levels of magnetic activity and emitting very little of the high-energy X-ray and ultraviolet radiation that can strip away a planet's atmosphere over time. This single characteristic transforms Ross 128b from just another candidate into one of the most promising nearby worlds for potential habitability. The advantage of orbiting such a quiet star cannot be overstated. A planet's atmosphere is its shield and its climate regulator. Without a substantial atmosphere, even a world perfectly positioned in the habitable zone would be a barren wasteland, unable to retain liquid water or protect surface life from cosmic radiation. The constant bombardment from a flare-happy star like Proxima Centauri acts like a relentless sandblaster, gradually eroding a planet's protective gaseous envelope into space. Ross 128b, by comparison, enjoys a far more gentle existence. Its atmosphere, if it ever formed, has had a much greater chance of surviving for billions of years. This stability provides a crucial window of opportunity for the complex chemical processes that could lead to the emergence of life to unfold without being reset by a catastrophic stellar outburst. This distinction forces us to refine our search parameters. For a long time, the primary focus was on finding a planet in the Goldilocks zone, the region where temperatures are just right for liquid water. But Ross 128b teaches us that we must also find a Goldilocks star. It's not enough to be in the right place, you also need the right kind of stellar parent. A calm, mature red dwarf like Ross 128 offers a steady, long-lived source of energy with a lifespan of trillions of years, far exceeding the 10 billion-year lifespan of a star like our Sun. This incredible longevity provides an almost unimaginable amount of time for life to arise, evolve, and potentially develop intelligence. While the planet is likely tidally locked with a permanent day and night side, the stable radiation environment means that any atmosphere it possesses could effectively circulate heat, potentially creating a temperate band in the twilight region. Ross 128b represents a quieter, more patient avenue for life in the cosmos, one that prioritizes long-term stability over dramatic energy, offering a compelling vision of a world where biology could have been given the peace and time it needed to flourish. Now we turn to a system that seems pulled straight from the realm of science fiction, where a pair of planets share a sky with not one but two suns. Meet Kepler 296e and Kepler 296f, orbiting within a binary star system located over 1,000 light-years away. This isn't a system where planets circle a single star with a distant companion. Here, the two stars themselves are locked in a mutual dance, orbiting a common center of gravity, while the planets orbit both stars together. This creates a celestial environment of stunning complexity and beauty. Imagine standing on the surface of either of these worlds and looking up. You would see two suns of different sizes and colors crossing the sky in an intricate, predictable rhythm. Some days you might experience a double sunset where both stars dip below the horizon in a spectacular display of fading light. Other times, one sun might be high in the sky while the other is just rising, casting long, intersecting shadows across an alien landscape. The very definition of a habitable zone in such a system becomes a fascinating puzzle. Instead of a simple, circular band around a single source of light and heat, the zone is shaped by the combined and varying energy output of both stars. The two stars in the Kepler 296 system are a larger, brighter orange dwarf and a smaller, dimmer red dwarf. As they orbit each other, the total amount of energy reaching the planets fluctuates. Kepler 296e, the inner of the two habitable zone planets, receives a substantial amount of this combined light, placing it on the warmer edge of the life-friendly region. Its sibling, Kepler 296f, orbits further out, experiencing a cooler, more subdued climate. This dynamic energy input could create seasons unlike anything on Earth, driven not by a planet's axial tilt, but by the changing proximity and alignment of its two parent suns. The potential for life under such exotic conditions is a thrilling thought experiment. Any plant-like organisms would need to be masters of adaptation, capable of photosynthesizing under a wildly varying spectrum of light as the two stars move through their dance. Their foliage might not be a simple green, but could shift color or even go dormant depending on which star is dominant in the sky at a given time. The daily and seasonal cycles would be incredibly complex, potentially leading to life forms with highly flexible metabolisms or sophisticated biological clocks to anticipate the changing conditions. The constant variation in light and energy could be a powerful engine for biodiversity, creating a multitude of ecological niches and driving rapid evolutionary change. On a world with two suns, life wouldn't just adapt to a single environment. It would have to thrive in a world of perpetual, rhythmic transformation. The stability of the planet's orbits in this gravitational ballet is another key factor. While it might seem chaotic, binary star systems can have regions where planetary orbits are perfectly stable over billions of years. The fact that we have found multiple planets in the Kepler 296 system suggests these worlds have found a harmonious path, a testament to the intricate balance of gravitational forces. This stability is essential as it provides the long-term consistency needed for life to emerge and evolve. The Kepler 296 system expands our understanding of where life could take root, demonstrating that habitable environments are not confined to solitary stars like our Sun. They can flourish in more complex stellar families, proving that the universe's creativity in crafting potential homes for life is even more boundless than we once imagined. Our journey now takes us to a world whose discovery was a technical triumph, a super-Earth that forced astronomers to push their instruments to the absolute limit. HD 85512b, located about 37 light-years away, was found using the same radial velocity method that detected many early exoplanets, but this discovery was different. It was one of the first truly Earth-mass planets found within a habitable zone, a detection so delicate it sat right on the threshold of what was possible at the time. This world, with a mass estimated to be about 3.5 times that of Earth, orbits an orange K-type star, a sun slightly cooler and smaller than our own. But its orbital path is what makes its story so intriguing and precarious. HD 85512b doesn't orbit in the comfortable middle of the life-friendly region. Instead, it skims the inner edge, clinging to the very brink of the habitable zone like a climber on a narrow ledge. A year on this world is a blisteringly fast 54 Earth days, a testament to its proximity to its stellar parent. This close-in position means the planet receives significantly more stellar energy than Earth does, about 40% more. At first glance, that would seem to push it over the edge into a Venus-like runaway greenhouse scenario, a world too hot for liquid water to survive on its surface. But here is where the story takes a fascinating turn, one that introduces a critical and often overlooked factor in planetary science, the power of clouds. The potential habitability of HD 85512b hinges almost entirely on a concept known as the albedo effect. Albedo is simply a measure of how much light a surface reflects. Fresh snow, for example, has a very high albedo, reflecting most sunlight back into space, while dark ocean water has a low albedo, absorbing heat. This principle, when applied to an entire planet, becomes a powerful global thermostat. The pivotal question for this world is whether it can generate a substantial cloud cover. Sophisticated climate models have shown that if HD 85512b possesses an Earth-like atmosphere and can maintain a cloud cover of at least 50%, those clouds would act as a gigantic planetary-scale sunshade. The white, puffy tops of clouds are incredibly reflective. By bouncing a significant portion of the incoming stellar radiation back into space before it can heat the ground, this cloud layer could effectively counterbalance the intense energy from the star. It would be a natural feedback system where increased evaporation from warmer oceans would create more clouds, which would in turn cool the planet, maintaining a stable equilibrium. In this scenario, the planet could enjoy temperate conditions suitable for liquid water, despite its seemingly hostile location. This transforms our view of HD 85512b from a likely scorched world into a potential paradise. Imagine a planet with extensive, shimmering oceans, but with a sky that is almost perpetually overcast. The cloud cover would likely be thick and global, creating a diffuse, soft light on the surface below. The climate might be warm and humid, perhaps even tropical across much of the globe with frequent rainfall. Life on such a world would evolve under a filtered sky, with plant-like organisms potentially adapting to lower light levels. The high humidity and constant cloud cover could lead to incredibly lush and dense ecosystems. This vision highlights that a planet's climate is not just a product of its distance from its star, but a complex, dynamic system where atmosphere, geology, and even biology interact. HD 85512b stands as a powerful lesson that the search for life is not just about finding a planet in the right place, but about understanding the intricate machinery of its global climate, where something as simple as a cloud can make all the difference between a sterile rock and a living world. Now we arrive at a system that offers a fascinating glimpse into a cosmic balancing act, a delicate interplay between two very different kinds of worlds that could determine the ultimate fate of a potentially habitable planet. Just 16 light-years away, the star Gliese 832 hosts a planetary family that feels strangely familiar, almost like a scaled-down mirror of our own solar system. The first member of this family is Gliese 832b, a gas giant with a mass at least half that of Jupiter, orbiting its star in a wide, looping path. The second, and the focus of our attention, is Gliese 832c, a super-Earth with a mass at least 5 times that of our own world, situated squarely within the star's habitable zone. This pairing, a rocky world in the life-friendly region and a giant planet further out, is a configuration that immediately captures our interest because it echoes the architecture of our own cosmic home. The presence of a Jupiter-like planet in a system is a double-edged sword for habitability, and Gliese 832b plays both roles. On one hand, a massive outer planet can act as a celestial guardian, a gravitational shield for the inner rocky worlds. In the early, chaotic days of a solar system, the system is filled with countless asteroids, comets, and other debris left over from planet formation. A giant planet's immense gravity can act as a vacuum cleaner, sucking up or flinging many of these dangerous projectiles out of the system entirely. By clearing the neighborhood, it reduces the frequency of catastrophic impact events on planets like Gliese 832c. In our own solar system, Jupiter is thought to have played this protective role, potentially giving Earth a more stable environment for life to evolve by lowering the odds of a civilization-ending asteroid strike. In this optimistic view, Gliese 832c enjoys the benefits of a massive body policing the outer system, creating a safer, more predictable environment. However, the Guardian can also become a disruptor. The gravitational influence of a giant planet is not always gentle or benevolent. If its orbit is not perfectly circular, or if it interacts gravitationally with other planets, it can have the opposite effect. Instead of stabilizing the system, it can inject chaos, perturbing the orbits of smaller inner worlds over millions of years. This gravitational nudging could push a planet like Gliese 832c out of the habitable zone entirely, sending it on a path that swings it alternately too close and too far from its star. It could even destabilize its rotation, leading to extreme axial tilts that cause wild climatic swings. The long-term stability of Gliese 832c, therefore, depends critically on the precise orbital dynamics between it and its giant sibling. It's a celestial dance where one misstep could have planetary consequences. Now, let's turn to the world itself. Gliese 832c orbits its red dwarf star in a mere 36 days, a tight, fast circle that places it firmly in the habitable zone. But this proximity comes with the usual caveats for red dwarf systems. The planet is likely tidally locked with a permanent day side and night side. The amount of energy it receives is similar to what Earth gets from the Sun, but it arrives as a constant, dim, reddish glow. The planet's substantial mass, however, is a significant mark in its favor. This super-Earth gravity would be highly effective at holding onto a thick atmosphere, which would be essential for distributing heat from the hot day side to the frigid night side, potentially creating a temperate band in the twilight region. A robust atmosphere would also offer protection from stellar flares, which, while Gliese 832 is relatively stable, are still a fact of life for red dwarfs. So, what is the final verdict on this world? Is it a protected paradise or a gravitationally threatened outpost? The answer is still hidden within the subtle mathematics of its orbit. Current data suggests the system is stable, but the margins may be fine. The presence of the giant planet adds a layer of fascinating complexity to its story. It invites us to consider that a planet's potential for life isn't just about its relationship with its star, but also about its relationship with its planetary siblings. A habitable world exists within a network of gravitational influences, a cosmic ecosystem where the actions of a distant giant can be as important as the warmth of a nearby sun. Gliese 832c stands as a compelling example of this interconnectedness, a reminder that the search for life is not just about finding a solitary island in space, but about understanding the entire archipelago in which it resides. As we bring our cosmic tour towards its conclusion, we return to a familiar name with a renewed sense of purpose. Kepler 452b, that ancient Earth's cousin we discussed earlier, is poised to transform from a statistical marvel into a real object of study. The James Webb Space Telescope represents a quantum leap in our observational capabilities, and planets like this are at the very top of its target list. The primary goal is to perform a detailed atmospheric reconnaissance. Webb's powerful infrared instruments are designed to analyze the starlight that filters through the planet's atmosphere as it passes in front of its star. By dissecting that light into a spectrum, scientists can search for the chemical fingerprints of specific gases. The Holy Grail would be the detection of a biosignature, a gas or combination of gases that is difficult to explain without the presence of biology. The simultaneous presence of oxygen and methane, for instance, is a powerful indicator on Earth, as these gases react with each other and would need to be constantly replenished, likely by living organisms. But even if no clear signs of life are found, the data will be transformative. Is the atmosphere thick with carbon dioxide, suggesting a runaway greenhouse effect like Venus, or does it show signs of water vapor and a temperate climate? The observations from Webb will finally answer the question of whether this 6-billion-year-old world is a verdant paradise or a scorched relic, providing a crucial data point for understanding the long-term evolution of Earth-like planets. Next, we shift our focus to a world where atmospheric studies are already underway, offering a preview of the discoveries to come. K23d is a super-Earth orbiting a quiet, cool star about 150 light-years away. What makes this planet particularly significant is that it was one of the first of its size to have its atmosphere probed by the Hubble Space Telescope. While the data wasn't detailed enough to identify specific molecules, it did confirm that K23d possesses a substantial atmosphere, a critical first step. This world is larger and warmer than Earth, receiving about twice the stellar flux, which places it on the inner edge of its habitable zone. This has led to speculation that it could be a mini Neptune with a thick, hydrogen-rich envelope and no true surface, or it could be a rocky super-Venus with a crushing, hot atmosphere. The excitement around K23d lies in its status as a perfect benchmark. It's a prime early target for the James Webb Space Telescope, which will have the sensitivity to break its atmosphere down into its constituent parts. By studying a world like this, which occupies a climatic middle ground between Earth and Venus, astronomers can learn how planetary atmospheres behave under intense stellar heating. The results will help us interpret data from other, more Earth-like worlds, teaching us how to distinguish between a life-bearing atmosphere and a sterile one. K23d is a key that will help unlock the secrets of many other planets on our list. Our final stop on this journey among confirmed worlds brings us to a nearby neighbor with a remarkable pedigree. Lyten b orbits a small red dwarf star just 12.2 light-years away, a stone's throw in galactic terms. This planet holds an exceptional distinction. It has one of the highest Earth Similarity Index scores ever calculated, a staggering 0.91, making it a near twin to Earth in terms of size and the energy it receives from its star. Its mass is only about 3 times that of Earth, strongly suggesting a rocky composition, and it sits comfortably within the heart of its star's habitable zone. But Lyten's star itself adds another layer of intrigue. It possesses a very high proper motion, meaning it is moving relatively quickly across our sky compared to other stars. This might seem like a minor detail, but it has profound implications for the future. This rapid motion makes the Lyten system an ideal candidate for an ambitious future mission known as the Starshot Initiative. This concept envisions sending tiny, laser-propelled nanocraft on a flyby mission to the nearest stars at a significant fraction of the speed of light. Lyten's star, with its high proper motion, will actually be moving closer to us over the coming millennia, making it a more accessible target. While we won't be sending probes there anytime soon, this celestial trajectory ensures that Lyten b will remain a key target for centuries, a beacon for future generations of explorers. It represents not just a world we can study with telescopes, but a destination we might one day, however distantly, strive to reach. As we reach the 30th and final entry on our list, we step across a fascinating threshold from the known to the unknown, from confirmed discovery to the breathtaking potential of what is yet to come. This spot is reserved not for a single world, but for a concept, a future category of planets that our current telescopes can only hint at. These are the speculative and hopeful worlds, the ones that will be revealed by the next generation of astronomical observatories, instruments so powerful they will transform points of light into landscapes of possibility. Our journey so far has shown us an incredible diversity of planets, but the most profound discoveries are likely still ahead, waiting for the tools that can see them. The key to unlocking these secrets lies not just in finding more planets, but in learning to read their atmospheres. This is the primary mission of the James Webb Space Telescope, which is already revolutionizing our understanding. Webb's incredible sensitivity to infrared light allows it to act as a cosmic chemist, analyzing the faint starlight that filters through an exoplanet's atmosphere during a transit. By dissecting this light into a spectrum, scientists can identify the unique fingerprints of specific molecules. The ultimate goal is to detect a combination of gases known as a biosignature, a chemical imbalance that is difficult to explain without the presence of life. On Earth, the simultaneous presence of large amounts of oxygen and methane is a classic example. These gases react quickly with each other, so their persistent coexistence suggests something, likely biology, is constantly replenishing them. Finding a similar signature on a distant world would be the most compelling evidence we could hope for, short of a direct signal. But the quest doesn't end with Webb. Looking further into the future, missions like the European Space Agency's PLATO observatory, planned for launch in the 2020s, are designed with a specific and ambitious goal: to find Earth-sized planets orbiting Sun-like stars in Earth-like orbits. While Kepler and TESS have been phenomenal at finding planets, many of the most promising candidates orbit smaller, fainter red dwarf stars because they are simply easier to detect. PLATO advanced cameras will stare at vast areas of the sky for years, with the precision needed to detect the incredibly subtle dip in light caused by a true Earth twin passing in front of a Sun-like star. It will build the catalog of prime targets for the next step, atmospheric characterization by the ground-based extremely large telescopes. These behemoths, like the 30-meter telescope and the extremely large telescope, with mirrors dwarfing any in existence today, will be able to directly image some of these nearby Earth-like worlds. They will attempt to separate the faint glow of the planet from the overwhelming glare of its star, allowing us to take our first crude pictures and analyze their atmospheres in even greater detail. This combination of space-based and ground-based power represents a coordinated scientific assault on the question of life in the universe. Perhaps the most exciting and speculative possibility, however, lies not with planets at all, but with their moons. Our own solar system has taught us that some of the most promising habitats for life are not the terrestrial planets, but the icy moons of gas giants. Europa, orbiting Jupiter, and Enceladus, circling Saturn, are frozen worlds with global, liquid water oceans hidden beneath their icy crusts, kept warm by the gravitational tug of war with their giant parents. Now imagine a similar moon, but orbiting a gas giant situated within the habitable zone of a distant star. This concept of an exomoon offers a paradigm shift in our search. A gas giant itself may be uninhabitable, but a large, rocky moon with a subsurface ocean could provide all the necessary conditions for life, while also benefiting from the stability of orbiting a massive planet. The gravitational forces that heat the moon's interior could drive geological activity, creating hydrothermal vents on the ocean floor, environments that on Earth are teeming with life entirely independent of sunlight. The search for these exomoons is incredibly challenging, but it is now a serious scientific endeavor. Astronomers are developing techniques to detect the subtle gravitational wobble a moon imparts on its host planet, or the slight variation in the timing of a planet's transits caused by a moon tugging it back and forth. Finding one would open up an entirely new frontier of habitable real estate in the galaxy. It suggests that life could thrive in the darkness of a subsurface ocean, illuminated only by the faint geothermal glow from below, with a gas giant hanging impossibly large in a black sky. This speculative vision reminds us that life may be flourishing in the most unexpected places, on worlds we are only just beginning to imagine. The 30th planet, therefore, is a placeholder for hope and for the boundless potential of discovery, a symbol that our search has only just begun and that the greatest wonders are still waiting to be found. And so our grand tour of 30 potential abodes for life reaches its end, a journey that has taken us from the searing inner edges of habitable zones to the frozen twilight frontiers. We have stood on the terminator lines of tidally locked worlds, peered into the global oceans of Hycean planets, and marveled at the complex dance of planets with multiple suns. From our nearest neighbor, Proxima Centauri b, to the ancient sun-like star of Kepler 452b, the overwhelming message is one of staggering diversity. The universe is not merely peppered with planets, it is a master artisan crafting worlds in an endless variety of forms, super-Earths with crushing gravity, icy satellites hiding subsurface seas, and temperate rocky orbs bathed in the gentle glow of a red sun. This incredible menagerie proves that the potential for life is not confined to a single, narrow recipe. It is a testament to nature's ingenuity, suggesting that wherever energy, liquid water, and a handful of key elements can coexist, the spark of biology might just ignite. This journey marks a profound shift in our cosmic perspective. For most of human history, the question of other worlds was one of pure philosophy. We gazed at the stars and wondered if they held companions. Then, with the first exoplanet discoveries, the question became if planets were common, if other solar systems existed. Today, that question has been resoundingly answered. We now know that planets outnumber the stars in our galaxy, and our inquiry has evolved into something far more specific and thrilling. The central question is no longer if, but which. Which of these countless worlds has crossed the threshold from a barren rock to a living planet? Which atmospheres hold the chemical signatures of metabolism? We have moved from cosmic cartography to cosmic biology, from mapping the real estate to searching for the occupants. This is a monumental leap, one that places us on the cusp of potentially the greatest discovery in human history. The search for life beyond Earth is more than a scientific endeavor. It is a journey that speaks to the very core of our humanity. It is an expression of our innate curiosity, our drive to understand our place in the vast cosmic ocean. Finding even simple microbial life on another world would fundamentally reshape our identity. It would tell us that life is not a fragile, singular accident on a tiny blue dot, but a natural and perhaps common process woven into the fabric of the universe. We would cease to be cosmic orphans and become part of a grand, interconnected tapestry of existence. The implications are humbling and exhilarating, forcing us to reconsider everything from biology and philosophy to our own stewardship of this planet. The adventure is accelerating at a breathtaking pace. Every week, new data streams in from telescopes like James Webb, TESS, and soon, from the powerful ground-based observatories under construction. Each new observation refines our models, reveals new candidates, and brings us closer to that moment of discovery. This is not a story with a distant ending. It is unfolding right now, and you have a front-row seat. Stay curious, follow the latest headlines from space agencies and research institutions. The next groundbreaking announcement could be just a news cycle away. Look up at the night sky with a new sense of wonder, knowing that each pinprick of light could be the sun of a world with its own stories, its own landscapes, and perhaps its own inhabitants. We want to hear from you. After exploring these 30 incredible worlds, from the promising stability of Lytton B to the controversial mystery of GJ 581g, which one captured your imagination the most? Would you want to gaze upon the triple suns of GJ 667cc, or dive into the proposed global ocean of K218b. Share your thoughts and your favorite planet from our list in the comments below. Let's continue this cosmic conversation together. If you've enjoyed this journey to the frontiers of astrobiology, make sure to subscribe and hit the notification bell. Our channel is your launch pad to more cosmic adventures, where we'll continue to explore the wonders of the universe, from the mysteries of black holes to the latest revelations from the depths of space. The cosmos is calling, and the greatest discoveries are